Hey there. Aki here.
And Ruby, we're back.
We're digesting K3MT's way of working with admittance and impedance on a Smith chart. We'll use a chart for 50 ohm cable, with Z0 equals 50 ohms.
An inductive impedance has a coil and resistor in series. This one plots on the R equals 1, and J equals +1, circle and arc, meaning Z equals 50 plus J 50 ohms.
Admittance, Y, is 1 over Z. It's composed of conductance, G, equals 1 over R, and susceptance B, equals -1 over X. Its admittance plots at the other end of a diameter, drawn through the impedance and the chart center, on the 0.5 - J 0.5 circle and arc.
Small circles plot impedance, and squares plot admittance. The 50 ohm LR series circuit, and the 100 ohm LR shunt, have the same impedance and admittance in circuit design.
Here are 3 other impedance to admittance conversions. To calculate Y from Z, square the R and X values, add them. Then divide the R and X values by this sum, and make J negative. To calculate Z from Y, do the same with the G and B values.
Every impedance on the R equals 1 circle will plot as an admittance on its image circle we sketch here. We will see a special use for these unit circles.
Here's an impedance Z equals 3 plus J3. It's at the end of 50 ohm coax. The impedance changes along the coax at constant SWR, here about 4 to 1.
After 75 degrees of coax, it changes to about 0.3 - J 0.4. It's become capacitive. By moving diametrically across the chart, we find its admittance as about 1 - J 1.6.
At 75 degrees, we've overshot a tad. So these values are close approximations.
We've changed to admittance mode, so the value of Z0 is replaced by Y0, equals to 1 over Z0. In this example, Y0 equals 1 over 50 ohms, or 0.02 mhos, now called Siemens. So Y0 equals 20 millisiemens.
We can remove the capacitive susceptance, B, by placing an inductive shunt across the coax. A shunt of plus J 1.6, or 36 millisiemens, will do. The result is a non-reactive admittance of 20 millisiemens, a resistive load of 50 ohms, often a target of such manipulations.
But there is another way to do the same thing. Draw the plus J 1.6 arc, and drop a vertical line to the minus J 1.6 point. Then draw an arc about the outer circle, from this point, to the right side, where admittance is infinite.
This is a case of a short circuit. The arc specifies a shorted piece of coax, a stub, 32 degrees long. This will produce the same plus J 1.6 susceptance. The new assembly is as shown here. This is known as serial shunt, stub tuning.
We challenge you to find an antenna impedance that cannot be brought to 1:1 SWR this way. The answer is, none. Though everyone shoots for that holy grail of 1:1 SWR, good engineering sets a maximum value to be tolerated.
Here we show the target circle as a shaded region. With the proper length of coax, an impedance can be brought into the shaded area.
Here are 2 points measured for a dipole antenna. It's about 3/8 wave overall length, Both points can be brought into the shade by one piece of coax nearly 90 degrees long. These convert to equivalent admittances, and a shunt stub brings the admittance and impedance close to chart center, with an SWR of under 1.5 to 1.
Suppose the first length is shortened, and just reaches the shaded border. Then the final impedance can be brought to 25 ohms, not 50. The right length, which just reaches the center of the shading, renders final impedance to 50 ohms. A longer piece renders it to 100 ohms.
So this technique can not only bring a load to non-reactance, or resonance, but can convert it to any desired impedance. We hope this has given you a taste of how to work with admittances and impedance, so you can go forth and design all sorts of impedance matching systems.
This concludes our demo. You will find it and lots more in Mike's book. As of March 2022, sold by these retailers. Or
directly from Mike. Just Google K3MT books.
So till next time, this is Aki
and Kurubi, saying,
thanks for watching. Bye, for now.